So we left off last time saying that in a thermodynamically favored process, spontaneous, the entropy of the system and its surroundings is always going to increase. And that takes us to our second law of thermodynamics. The total entropy of a system and its surroundings always increases for our thermodynamically favored process. So that quantity of entropy is always going to be positive. Mathematically, at a given temperature, we can say that the change in entropy is always going to be greater than Q over that temperature. All right, so one of the things we like to look at is the entropy change for a phase change. Obviously going liquid or solid to liquid or solid to gas or liquid to gas, that is spreading the molecules farther apart, entropy is increasing. The molecular disorder is also increasing. So I can manipulate my equation, and instead of just delta S greater than Q over T, we know that Q is the same as delta H at a certain temperature and pressure, so I can say delta H over T. So what is the entropy change for the melting of 1 mole of ice? Well, the delta H fusion for water is 6 kilojoules per mole, which of course was experimentally determined. So our entropy is usually in joules per Kelvin, or joules per Kelvin mole. So I just switch that to joules, divide by the temperature that this is happening, 0 degrees Celsius, so 273 Kelvin, and I get 22 joules per Kelvin. And this is what we saw last time. Okay, 1 mole of ice has entropy of 41 joules per Kelvin. A mole of water is 63 joules per Kelvin. So the difference is my 22. So that's one type of question. Here's another question. If we're going to vaporize some carbon tetrachloride, and the liquid form has an entropy of 216 joules per Kelvin at 298 Kelvin, 25 degrees Celsius, what's the entropy for 1 mole of the vapor at this temperature? So again, I know delta S is equal to delta H over T. So I take my delta H of vaporization, switch it to joules, divide by my 298, and I get 132 joules per Kelvin. But remember, that is my delta S. That's my change in entropy as the liquid becomes the vapor. So the question that says, what is the entropy for the vapor? It accumulates. So for the gas, it's the 216 from the liquid plus my delta S of 132. And so we end up with 348 joules per Kelvin. One of the things we can do is predict the entropy change of a reaction. And we can do this because we kind of have an idea that the dispersal of energy creates more entropy. So we can typically say that delta S of a reaction is definitely going to be positive under these couple circumstances. One, when you create more stuff. Okay, for example, our decomposition reactions. A molecule is broken into 2 or more smaller ones. But pretty much any time when you have more moles of product than you do reactants, specifically with gas. So here we see the decomposition of ammonia. So yes, not only is this decomposition, but we also are going from 2 moles of gas to 4 moles of gas. This is also true when the volume of a gas. If we have a balloon this size and a balloon this size with the same amount in there, those particles are more dispersed, and so therefore there is more entropy in the larger volume situation. The last thing is what we were just talking about, phase changes. Solid to liquid or gas, or even to plasma, and the same with liquid to gas. So when you look at these reactions here, you can predict whether you believe the entropy would have a positive or negative value. So pause the video and try and see if you can figure out if it would be positive or negative, but also think about why. So our first one, we have solid glucose becoming liquid ethanol and carbon dioxide gas. So hopefully you said that this is a positive delta S. For a couple reasons. A single molecule is breaking apart, but also we're creating a gas from a solid. Both of those situations show an increase in entropy. Letter B, I've got the ammonia plus carbon dioxide making urea and water. Well, I'm going from gas things to a liquid solution. I'm also going from smaller molecules to a bigger one. So this would be a decrease in entropy. Liquid to gas, vaporization, definitely positive. This last one here now, I've got 2 moles of gas as reactants, 2 moles of gas as products, and all the particles, all the species are pretty small and similar in size. So this one we would say, can't predict that. All right, there's no way you can truly predict what that entropy change would be. It would have to be calculating using our standard entropy values. All right, so we keep going back to this. Will a chemical reaction go as written? Is it thermodynamically favored as written? And of course, at our constant temperature and pressure. So because of our second law of thermodynamics, we know that the change in entropy has to be greater than delta H over T. I rearrange that equation, rearrange it again, and we're going to see that this form of the equation, delta H minus T delta S, must be less than 0 in order for a reaction to be thermodynamically favored as written. All right, and so you can calculate delta H and delta S using our tables, and you've done this before, sum of the products minus the sum of the reactants, so we'll see that here in a second. So with this, again, when delta H minus T delta S is negative, that reaction is thermodynamically favored as written. If it is a positive value, it is not thermodynamically favored as written. The reverse process would be, but not as written. And of course, if we end up exactly at 0, that would be at equilibrium. So here we see, is the creation of ammonia from nitrogen and hydrogen thermodynamically favored as it is written at 25 degrees Celsius and 1 atmosphere? So here we see the delta H of formation values, remembering that our elemental forms in their standard state have a delta H of 0. And then we have our entropy values. And notice that our elemental forms are not 0. That makes sense. Gaseous nitrogen and hydrogen have entropy. They are gases. And so we don't see a 0 value there. Be careful also, our delta H values are typically given to us in kilojoules per mole. Entropy is joules per Kelvin, joules per mole Kelvin. So I can find my delta H by doing, again, the sum of the products 2 times, remember you're using the coefficient, 2 times the negative 45.9, and then minus 0. So my delta H for this reaction, negative 91.8 kilojoules. Do the same thing with S for the entropy, 2 times the 192.7, and then minus 1 of the 191.6s and 3 of the 130.6s. So I end up with negative 198 joules per Kelvin. But to plug it back into my equation, I do want to change that to kilojoules so it matches my delta H. And so now again, I want to know, is this thermodynamically favored as written? So my delta H minus T delta S must be negative in order for that to be true. And we do find that that is the case. My negative 91.8 for delta H minus T, this was at 25 degrees Celsius, so it's 298 Kelvin, times my delta S, which is 0.198 negative. And so yes, this reaction is thermodynamically favored. It ends up with a negative 32.8 kilojoule value. What we're going to see here is that this delta H minus T delta S has a special name, Gibbs free energy, and that will be next time. All right, see you soon.